We're going to start with going over the Flying Pig worksheet. Actually, did we go over the car side? We already go over this side? First one? Okay. So, if the car is accelerating from a stop, your body feels like it's moving backwards. It actually accelerates forward, and the force is forward. Okay? If the car hits the brakes, your body lurches or feels like it goes forward, like into the seatbelt. The car actually accelerates backwards in the direction of the force on the brake. Wow. Is that better? Why did you move? Were we getting away? To transport! Oh. That's what a good immune system is for, my friend. We'll see how good it is. You know, I've done interesting studies with kids that are like exposed to lots of dirt and germs and things when they're little, and they have much better immune systems. So just thank your friends, your very sick friends. All right, so the car accelerates backward, or you could also say it negatively accelerates forward if you wanted to. And the force is backwards, that's the force from the brake. Okay? That's what the vector should look like. Then, of course, this is when it starts getting interesting. Now the car goes in a circle. So your body leans outward, or it feels like you're leaning outward in this particular scenario. The acceleration is inward toward the center of the circle. The force is also inward. Okay? Here's what's really happening. The velocity is constant. So the number value, I shouldn't say the velocity, I should say the speed. The number value for the speed is constant. So if you looked at the speedometer of the car as it rounded this corner, it would stay the same. So how can it be accelerating if the speed or the speedometer stays the same? Go ahead.
It's accelerating in a different direction.
Right. It's accelerating through a change in direction. And that's a hard thing to mathematically quantify, so that's where that centripetal force equation that I wrote for you, that's where that comes in. That equation can be used to quantify the change in direction. What?
Well, would cars be able to take turns a lot sharper if you were able to turn the back wheels as well? So like back wheels turn this way and front wheels turn like that?
Oh, like so you could actually find, sure. Yeah, that would help with the friction. That would be, think about it if you were moving down the road. They do have cars that have independent axles, but they don't necessarily rotate like that. They just, it helps you not get stuck in the mud.
No, but if you were like driving, that's during the straight, the wheels go straight, but soon as you turn, they would go like this.
Right.
Like that.
They'd have to, but you'd have to be able to adjust specific to the length of the car, specific to the turn. Well, because the different radius turn, a tighter turn means you're going to have to turn those wheels at a different angle.
More like this they go.
You're just going to have a match but go the opposite direction. That would probably work.
Yeah, so like if you're turning, you can like turn the wheel and then you turn it, they turn like that.
Yeah, I'm following you. Go ahead and design that. If you can do it efficiently and cheaply, sure. Then you can take turns faster.
Yeah, but then it'd be even harder to get out.
It'd be harder to do what, Steve?
When your car fish tails, it'd be even harder to get out because every time you turn, it'll just amplify it.
Yeah, there are issues with that.
Put the spikes on the tire.
All right. Let's move on. Now we're going to do the swinging ball over your head problem. So the kid whirls, this is a rock over his head, the whirling stone, the motion keeps changing, so if you spin it faster, the direction change would also be faster. This means that as speed increases, acceleration increases. By what relationship is that increase? In other words, is it linear, exponential, logarithmic, inverse? We do know.
I know.
It is exponential. How do you know that, Greg?
Because if the velocity
It was a good guess. Look at the equation. Look at the equation on the board in blue. Centripetal force. Right. Right. So that equation guides the relationship between centripetal force and speed. So in other words, if we doubled the speed of this swinging rock, how many times would the force increase? Go. 4 times. Right. Nice. Conversely, if we decrease the radius, so make the string shorter, then it's like a tighter curve.
Which means the acceleration will be avoided.
Yes. So the acceleration increases when the radius decreases. How is that relate? That's a what kind of relationship? When one goes up, the other goes down. Inverse, right? Yes. No. This actually, I found this worksheet. This is so weird. I found the pig and the worksheet and the accessories separately, all independently. It was meant to be. So, and then I created a whole lecture around those 3 things.
Wait, but that pig is come up like this.
I know. Well, there's other flying pigs in the world. I don't have the only flying pig.
So there are 5 flying pigs?
Yeah. Put on the airplane, Elvis.
Yes, there are flying pigs. I mean, independently flies by itself.
Remind me, I have a quirky video about a flying sheep. So that's, I don't think we'll have time
Wait,
today,
were
but
you going to show us a video yesterday that you can stream to us today?
maybe. Can't
Sure,
remember.
today, while I was gone.
Maybe while you're working, I'll put up the flying sheep video. Okay.
Okay.
All right. Now, flying pig. Flip over your page. The pig, if you think about the string, it sort of creates like a cone shape. And if you were to take the tension in the string and resolve it into its horizontal and vertical vectors, what would the relationship be between, and that's really what question 1 says, if somehow you were to replace tx and ty, the pig would behave as if it was just supported by t. Because where do tx and ty come from? T, yeah. So that's, sure, take out t, and as long as you can leave tx and ty, everything will be the same. Number 2, the pig doesn't accelerate vertically because?
Gravity.
That's true, Wes. Nice catch. What's true about gravity and ty?
Equal and opposite.
Equal and opposite. Thank you, Andrew. Velocity of the pig at any instant is tangent to the circle, and since the pig continues in a circle, tx must be the centripetal force. That's the equation that it's equal to, and tx points along the radius. Okay? And then for those of you who are parallelogrammably challenged, that's the parallelogram. A parallelogram has two sides. These 2 vertical sides are parallel, and then t is parallel, so I just drew these in. The resultant, the diagonal of that parallelogram, is what pulls toward the center of the circle. So the resultant lies horizontal, it pulls toward the center, and it is centripetal.